Our everyday lives have changed profoundly in the last 20 to 30 years. Computers, electronics and the internet have transformed our ability to access information and process data quickly, in our homes, at work and globally. What kind of physics underlies this revolution? What is actually inside a computer? And do scientists have any idea what future generations of technology might look like? We may be on the threshold of a new technology, where we have to take fundamental physics very seriously when designing computers. At the Niels Bohr Institute, we are working with quantum electronics, which combine the latest nanotechnology and the most basic physics, quantum physics. But before we look more closely at this research, let us first take a look inside a regular computer. Here's the heart of a computer, a microprocessor. It's a small chip with millions of electronic connections that transmit signals around the circuit. The signals are made up of electrons that flow along these microscopic highways and represent the computer's nerve impulses. It's largely the number and size of the individual elements, such as transistors, as well as how compact the circuit can be made that determines how fast a computer can work. It's all about the electrons and how they can move. Electrons are the particles that orbit the nucleus of all atoms. A hydrogen atom has 1 electron, helium has 2, a gold atom has exactly 79, and so on. But in solid matter, and especially in metals like copper or gold, some electrons can break free from the nuclei and move more or less freely through the material. An electric current in a wire is made up of those free electrons. Normally, we do not think of electric current as individual electrons, but rather as a river of charge, like water in a pipe. But what happens if the wires are made ultra small? Can we observe the individual electrons? Can a single electron constitute a current? And most importantly, can you create new technologies based on the unique properties that the electrons possess when they live in the atomic world described by quantum mechanics? To answer these questions, we produce nanometer-thin wires called nanowires in a laboratory. The wires are grown in a special vacuum chamber at 500 degrees. First, small gold particles are spread on the surface, and then beams of different kinds of atoms are directed towards the surface, where they collect in the gold particles. A single nanowire grows out of each particle. The wires are less than 100 nanometers in diameter, 1,000 times thinner than hair. Here's an image of a forest of nanowires that grew somewhat randomly. Let's take a closer look at one of the wires. We make a cross-section of a wire and zoom in 10,000 times. This is an actual picture of a nanowire taken with a special electron microscope. Now we see the individual rows of atoms. All the atoms sit in a neat, orderly pattern. The wire here is made up of 2 kinds of atoms, indium and arsenic alternating, resulting in different contrasts of the spots. Let's follow a single row of atoms, indium, arsenic, indium, arsenic, neatly arranged in a zigzag pattern. Something happens here. The nanowire has a stacking fault. A row of atoms is shifted in relation to the others. If the nanowires have this kind of random error, they will all behave differently. This is a problem if we need to understand and use the materials for sensitive quantum electronics. You cannot build a functional circuit of 100 transistors if they all behave in different ways. Then each transistor would be its own little research project. That's the situation today. But in recent years, we have managed to produce quite orderly forests of nanowires without faults. We now have the perfect material to move forward with the exploration of quantum transistors. I'm holding an electronic component based on nanowires. This device is made in the research laboratory. It only contains a single transistor and is therefore only suitable for scientific research. Here's a picture of the little microscopic transistor made from a single nanowire. A transistor is basically a valve for electricity. With advanced techniques, different metal electrodes are pasted onto the nanowire so we can send an electric current through it and control the electrical signals. Now we can measure the electrical current that can flow through the wire. The graph shows the current as a function of the voltage of one of the thin metal electrodes we saw before. We see a series of peaks on the graph, short current pulses. Each of these indicates that an extra electron has jumped onto the nanowire. By making circuits using these kind of components, we can count and actually control the number of electrons in the wire. When we make transistors based on individual elementary charges, we move away from standard electronics as we know it today and towards a world of atoms. Here there are different rules than we're used to. Here it's the atomic physics and the so-called quantum mechanics that are describing reality. Quantum mechanics can be difficult to understand, difficult to grasp, but it offers endless possibilities for new technologies based on completely different principles than those we are used to. Most people have heard that all the information in a computer is stored as zeros and ones, binary numbers. This corresponds to each transistor either being turned on or off. There are only two possible states. Quantum mechanical systems are different. They can exist in so-called superposition, a kind of mixed state, not just a 0 or a 1, but both at the same time. For an electron in this energy landscape, this could mean that it's not just to the right or left, but a bit in both places at the same time. If we have more than one electron, quantum mechanics gives even more options. For example, you can construct situations where the two particles are so closely connected that even if you separate the electrons, a measurement performed on the one electron will affect what we see the other electron does. This phenomenon is called entanglement. In a laboratory, we are working to realize this kind of twin states where more electrons or transistors in a circuit feel this quantum entanglement. During the last century, science was preoccupied with interpretations of quantum mechanics. Now we are trying to use the new effects in practice. Even though quantum physics can seem a bit mysterious and incomprehensible, it doesn't prevent us from using it. It's a theory that works, and it's important for understanding all materials, chemical reactions, the properties of light, and much more. But how can the laws of quantum mechanics, like the superposition principle of electrons, be used in electronics and computers? Let us return briefly to the computer as we know it. In an ordinary computer chip, all information is stored as zeros and ones, called bits, corresponding to the transistors being turned on or off. In a computer, any action or operation performed on a binary number results in a new binary number. If we instead imagine a chip comprised of quantum transistors, it opens up for new possibilities. What was previously bits now become quantum bits, qubits, and a chip could contain a superposition of information equivalent to an entire collection of binary numbers at once. In this chip, an operation could work on all these numbers at once, all in parallel. For each operation, we would solve 100, 1,000, or even more calculations instead of one. This example gives an idea of why a quantum computer could have such a huge processing power, much greater than any ordinary machine. No one knows if and when it will be possible to make a usable quantum computer. But one can imagine many other applications of our quantum electronics. For example, for instruments used for extremely sensitive measurements. The ultra-thin nanowires can be used for more than just elements in electronic circuits. For example, it has also been possible to use them for solar cells that are extremely efficient at converting light into electricity. Another example is biosensors that can be coupled with living biological cells and can measure the processes taking place in the cells. In the image, we see a forest of our nanowires. Biologists have helped grow living cells on the wires. These are the big soft blobs on top of the wires. The situation is a bit like a fakir on a bed of nails, although the aim here is to get the sharp nanowires into the cells so you can probe their behavior. The cells themselves are microscopically small, less than 1/100th of a millimeter. The image gives a sense of how small and thin the nanowires really are. Let us return to our theme, quantum electronics. As we have seen, quantum mechanics is completely different from our usual physics. The same applies to the quantum computer. It's not about creating a machine that is 10 or 20 times faster than what we have today. It's about radically new principles, and it's therefore expected that it will be possible to solve problems that there's no chance of addressing today. For example, the structure of complex proteins that are important for understanding how molecular biology works. If we want to develop the technology of tomorrow, we have to dive deep into the physics. We are well on our way to understanding the basic requirements and principles for a quantum computer, and the required materials are continually being perfected in the laboratories. Time will show whether the nanowires from the Niels Bohr Institute are the answer to the computers of the future and quantum electronics.